Hello and welcome back. In part 1 of this series of videos we saw how a neutron star is the core of a star that remains after the rest of the star has blown itself apart in a supernova explosion. The core has been compressed by gravity into a sphere perhaps 10 or 15 miles across, consisting largely of neutronium, a bizarre element with a density so high that a teaspoonful of neutronium would weigh 4 billion tons. In part 2 we're going to start looking at different types of neutron stars. Not so long ago astronomers thought that classifying them was easy and that they could be placed in just a couple of categories. But like so many astronomical phenomena, the situation is more complex, and it's turned out not to be an easy task to pigeonhole neutron stars after all. As we're finding out, it seems there is more diversity in neutron stars than we used to think. However they behave, all neutron stars have a few things in common. They are all around the same size, with variations in size accounted for by differences in the original mass of the star which gave birth to them, which is known as the progenitor star. They all rotate, but with huge variations between the slowest rotating and the fastest rotating neutron stars yet discovered. The rotation of a neutron star is so constant, so unchanging, that if you were to use it as a timepiece, it would rival or even exceed the accuracy of the best atomic clocks we can build. And lastly, all neutron stars possess a magnetic field, but again with huge variations in the strength of the field. The first type of neutron star we'll look at is known as a pulsar. A pulsar is the name given to a neutron star where particles surrounding the star are accelerated by the intense magnetic field towards the magnetic poles, where they are focused into beams or jets of energy, which shoot out from the poles at about 70% of the speed of light. Note that the magnetic poles are often not aligned with the neutron star's axis of rotation, meaning that the jets describe a cone as they sweep round the sky. In other words, they wobble. If the Earth happens to intercept one of these jets, we see a flash. If it doesn't, we see nothing, meaning that there is almost certainly a huge number of neutron stars we never see. And the only way we can see pulsars is by their flashes. They're far too small, just a few miles across, to see even in the largest telescopes. The vast majority of neutron stars are pulsars, and most of them emit their beams in the form of radio light and are therefore known as radio pulsars, detectable with radio telescopes. However, this is not the whole story. Pulsars can emit visible light, gamma rays and X-rays in the form of jets. It is thought that all pulsars emit these types of radiation when they are young, but over time they lose energy and emit just radio waves. What type of energy we detect from a pulsar is therefore a guide to its age. For example, a typical 10 million year old pulsar will probably just emit radio waves. Let's look at an example. In the year 1054 AD, Chinese astronomers observed what they called a guest star in the heavens. They wrote that it was as bright as Venus and visible in daylight. Accounts vary as to how long this guest star was visible for, but one record states it was visible for a whole year in the sky. Others, however, disagree, citing a much shorter period. The Chinese refer to the object as being below Tianhuan in the sky. We know Tianhuan to be a star in the constellation of Taurus, and we now believe that what they witnessed in 1054 was a supernova explosion. And we also know what is in that same position in the sky today, the Crab Nebula M1 in Messier's famous catalogue of celestial objects. The Crab Nebula is a supernova remnant some 6,500 light years away, and it spans 11 light years. At its heart is a pulsar, one of the first discovered back in the late 60s. Its beams sweep by the Earth 30 times a second, meaning of course that the Crab pulsar rotates at that speed, 30 times a second. But the pulsar is one of a small group which also flashes in optical light as well as at radio wavelengths. Slowed down from its actual rate of 30 flashes per second, here the Crab pulsar betrays itself by flashes of visible light emitted as jets from its magnetic poles. The fact that it emits both radio and optical light indicates a young pulsar, one barely 1,000 years old. But there's more. At the heart of the Crab Nebula there are high-energy particles produced by the pulsar that glow in X-ray light. This time-lapse video taken by NASA's Chandra Orbiting X-ray Observatory shows dynamic rings, wisps and jets of matter and antimatter around the pulsar in the Crab Nebula. The time-lapse was made from 7 still X-ray images taken by Chandra between November 2000 and April 2001. In addition, the presence of high-energy X-ray emissions in the jets shooting out from its poles marks the Crab Pulsar as young. In pulsars millions of years old, we see just light at radio wavelengths, an indication that energy levels around the pulsar are less intense and its magnetic field weaker, no longer able to accelerate particles like electrons and positrons to sufficiently high levels to produce X-rays and gamma rays. Notice how the jets of X-rays emitted from the pulsar are corkscrewing around, indicating its magnetic field is not aligned with its axis of rotation. And there's something else. As energy is removed from the system by the lighthouse-like beams, the pulsar's rotation rate slows down. Although over short periods the steady ticks of pulsars are the most accurate clocks in the universe, over long periods the pulsar spins slower and slower. This has actually been measured for some pulsars. Energy is also removed from the system in the form of gravitational waves, but we'll talk about those in another video. This is the Velar Pulsar, the first ever discovered. It spins 11 times per second and emits radio-optical gamma and X-ray radiation. The sound you are listening to is its radio emissions, that fast ticking as the Earth intercepts one of the pulsar's jets 11 times per second. Notice again the corkscrewing X-ray jet. There is a class of pulsar known as millisecond pulsars which complete one rotation in less than 10 milliseconds, 1 millisecond being 1,000th of a second. Millisecond pulsars have been detected in radio X-ray and gamma ray light. The current record holder for this incredible rate of rotation is the pulsar PSR J1748, which rotates at an amazing 716 times per second. So the question is, why do these pulsars rotate so quickly? What's the mechanism involved? Well, a millisecond pulsar is the result of a system where the pulsar has a companion star, in other words, a binary system. In this NASA animation of such a binary system, we see a pulsar and its companion, which is a normal star. Both co-orbit around their common centre of gravity. The intense radiation wind from the pulsar strips material from the surface of its companion, which is then pulled onto the neutron star by its intense gravity. As this material falls onto the surface of the neutron star, the laws of conservation of momentum mean that the neutron star will spin faster as a result. The infalling material from the companion is heated up to millions of degrees by the pulsar's intense magnetic field, causing blasts of X-rays that can be seen across the universe. When we see X-rays in the universe, it's always an indicator of extremely high temperatures. This type of pulsar is therefore known as an X-ray binary. But there's a periodicity to this activity. After perhaps a few weeks of intense X-ray emissions, the pulsar's magnetic field reconfigures itself to act like a barrier against the infalling material which is deflected around the pulsar. The X-ray emissions cease and we don't see anything. However, when the amount of material dragged off the companion star builds up to reach a sufficient amount, the magnetic field collapses under its pressure, heats up the material and the X-ray blasts resume. Binary X-ray pulsars are therefore characterized by this on-off X-ray emission. The material continues to fall onto the pulsar, eventually speeding it up to spin once in less than 10 milliseconds. The acceleration of the pulsar's rotation speed does not happen overnight. It occurs gradually over a long period, perhaps as much as 1 billion years. So what is the end of this process? Eventually, the accumulation of material and more significantly the intense wind of radiation from the pulsar, which removes material off the surface of its companion to then be consumed, completely destroys its companion star. The first of these binary X-ray pulsars, which eventually totally consume their companion, was discovered in 1988 and was given the rather fitting name of the Black Widow Pulsar. It's located roughly 6,500 light-years from the Earth. It orbits with a brown dwarf or a super-Jupiter companion. The pulsar and its companion rotate around each other every 9.2 hours. In 2010, it was estimated that the neutron star's mass was at least 1.66 solar masses and possibly as high as 2.4, making it a candidate for the most massive neutron star yet discovered. The name Black Widow has since become the descriptive name for all pulsars of this type. Around 24 Black Widow pulsars have so far been discovered in our Milky Way galaxy. This is NISA, an experiment on the International Space Station. NISA stands for Neutron Star Interior Composition Explorer. Its goal is to observe X-rays from neutron stars in unprecedented detail so that astronomers can try and work out their internal composition. By timing with exquisite precision exactly when X-rays arrive as the neutron star rotates, astronomers have been able to create something that would have been unthinkable just a few years ago, a map of the surface of a neutron star. As we have seen, the conventional view of a neutron star is that its intense magnetic field is anchored at two magnetic poles, much like the Earth's, and indeed all the planets in the solar system which possess magnetic fields. Here we see that the magnetic poles are not perfectly aligned with the neutron star's geographical poles, but this is not unusual. The Earth's magnetic poles, for example, lie some distance from the North Pole and the South Pole. What is important here is that the neutron star has a north magnetic pole and a south magnetic pole located near to 0 degrees latitude in the northern and southern hemispheres respectively. This was an assumption based on the way we know magnetic fields behave wherever we have seen them generated from a body like a planet or indeed a star like our Sun. At the point where the magnetic field lines converge on the neutron star's magnetic pole, astronomers expect there to be a so-called hotspot, an area of intense X-ray release. But after a month spent processing NISA's X-ray data from a pulsar called J0030 with a supercomputer — it would have taken a desktop PC a decade to have crunched the data — astronomers finally had the first map of the surface of a neutron star, and they saw something extremely bizarre and completely unexpected. This then is the surface of pulsar J0030. The white markings are the hotspots, areas of intense X-ray release, where the magnetic field lines converge. Like the astronomers, you can immediately see that something is wrong. In the right-hand image there are not 2 but 3 hotspots. The 2 images here represent data acquired at different times, but in both it is clear that if the white spots do indeed represent the pulsar's magnetic poles, all 3 of them are in the southern hemisphere. And why are there 3 in one image but not in the other? In addition, one of the 3 hotspots is an elongated crescent-like feature, hence not really a spot. If it is a magnetic pole, it's unlike anything we've seen or even considered. If all 3 of the hotspots are magnetic poles, that would represent the presence of a magnetic field which is frankly bizarre and complex beyond our understanding at the moment. What does all this mean? Nobody really knows. But recently there has been an intriguing suggestion that we've been looking at things backward. Instead of the hotspots being caused by magnetic field lines converging on the surface, the hotspots are being generated from within the interior of the neutron star, welling up to the surface and then somehow attracting the magnetic field lines to them. If true, the NISA instrument is really living up to its purpose and telling us something important about what's going on inside pulsar J0030. But for now, this map of the surface of a neutron star is truly enigmatic and mysterious. Maps of other neutron stars will be needed in order to understand just what we are seeing. Well, that brings us to the end of this video about pulsars. We've only really scratched the surface here, but I hope you've enjoyed this introduction. Next time we'll be looking at what is undoubtedly the weirdest type of neutron star, the Magnetar. If you thought pulsars were strange, you've not seen anything yet. Please don't forget to like and subscribe. We'd love to keep bringing you more videos like this one, and only by you supporting us can we make that happen. Thank you so much. Don't forget the Space Oddities live programme on Mondays at 8 PM UK time for the latest astronomical news, discussion and chat. Until then, this is Andy of Space Oddities wishing you all the best. Until next time, bye bye.